we're now official. All right, so who wants to share? We talked about this yesterday a little bit, kinda, but let's make sure we really understand the boiling point of a liquid. Now, in this room, water has a normal boiling point of 100 degrees, because what's normal mean? At standard pressure. So in here, water could only be 100 degrees max. But if we change the air pressure in here, then the temperature would change. So the temperature can change based on the air pressure, but whatever environment the liquid is in, water for example, whether it's high pressure, low pressure, whatever that boiling temperature is, that's it. It'll never go above it unless you start changing the air pressure. Anyways, enough with me talking. Who wants to tell me why? Max, go ahead. Good, I need a little bit more. So water's it's boiling and it's evaporating, therefore turning into a gas, but why does that keep the temperature of the liquid the same? How come it doesn't keep going up and up and up, even if I give it more heat? Very good. When the liquid boils, it evaporates and takes any extra heat with it. What is it doing with that extra heat? It's breaking those forces of attraction, right? Because liquid particles are pretty close together, just kind of moving around a little bit. And then it takes that extra heat and it breaks those forces, turns into a gas, and then takes the heat with it. So therefore the liquid is regulated, keeps the liquid the same temp, and whatever that temp is, the boiling point. Okay? Good. What is dynamic equilibrium? Used to contain liquid. I know a lot of you know this. We just talked about it yesterday. Monique, go ahead.
That's when evaporation, condensation, and
Good. And same what? Rate. Very good. So we have evaporation, that's kind of going up, and then we have condensation going down, right? Both are occurring at the same rate. That's good. She used the word rate. That's what equilibrium really means. When two processes, whether it's a chemical or physical process, we're talking physical right now. We do chemical equilibrium later in the year, but it's the same definition. It's two changes happening at the same time, same rate, and that's what dynamic equilibrium is. And if it's contained, the vapor can't escape, so you're going to have condensation, evaporation at the same time. One more thing about that. In that container, so right here, okay, we have a contained liquid, you can't see it. Remember the guy in the video said it's not something you're going to be able to see, but it's happening. So you have evaporation, condensation. What's building up in here? What kind of pressure? Vapor pressure. Good. Remember what I called it? He didn't call it this. What's happening in here when two things happening at once? Equilibrium. So what kind of vapor pressure? It's called equilibrium vapor pressure. When there's an equilibrium reached in here, the vapor pressure is the max it's going to be. This bottle isn't going to just blow up. Okay, just sitting here, the pressure's not going to build, and it's just going to explode. Doesn't work that way because it's at equilibrium. So every time a whole bunch of particles evaporate, a whole bunch condense, so therefore it stays constant in here. That vapor pressure is constant. That's what equilibrium vapor pressure means. What causes vapor pressure? Who did I talk to yesterday about this? I forget, but Kaylin can tell us. What causes vapor pressure again?
increase in temperature.
If you increase temperature, the vapor pressure, yeah, if I heat this up, we're going to have a lot of vapor and a lot of vapor pressure. Good, but what just simply causes vapor pressure? Not how to increase it or decrease it. If you can't remember, it's okay.
I don't know.
All right, Earl, help her out.
Is it where like all the gas particles like collide and stuff?
Say the first thing you said.
All the
Vapor particles colliding, that's all it is. In here you have vapor particles bouncing all over the place. That's called vapor pressure. Okay, and I got one more quick question I'm going to pop up from the regents. Then we will go over the homework in the book. And then we'll go back and do the demos. And then take some notes. And then you have more homework. Sounds like a good day, doesn't it? All right. As soon as that pops up, I want you to answer it while I find the answers to the homework here. You can just do it in your head. Multiple choice question. Very common, I think pretty easy. I say easy at the risk of making someone not feel so smart, but I think everyone in here can get this. That's why I say easy. It's one of the easier questions you're going to see using what? Reference table what? H, right. So some of you may not even need to look it up because we talked about it a bunch. All right, we should have a winner. And the winner is Marcy. Yes, how do you know that, Marcy? Very good. On table H, ethanoic acid has the highest boiling point. So she knows that it has the strongest force of attraction. So who am I going to pick on now? Laura Griffin. This has nothing to do with boiling point, but that's a good way to answer it. Good job, Marcy. So why did they give us 50? Laura? Very good, good. So they want you to go, there's different ways to answer this, okay? But they want you to go to 50 degrees, and if you go to 50 degrees, you see that right here at 50 degrees, it is the lowest line, and what does that mean? We learn, and maybe you memorize, that means it's the strongest forces, but what else, how can you explain that to somebody? Like, how do you know, besides what Marcy said, how do you know this has the strongest forces? Okay, yeah, highest boiling point, good. But what else could we say? Someone besides Laura there. What does that mean, the lowest line? How does that help? Kara? How does that help us answer this? We know it's the lowest line.
Because the pressure is the lowest, it's lower than all the others.
Good, it has the lowest vapor pressure. What does that mean, Maddie? It has the lowest vapor pressure. Very good. So, you know, she could have just said, well, that means it has strong forces. I'm glad you didn't, because, yeah, we know that. That has strong forces, and what does that mean? It takes a long time to evaporate, which means it has strong forces, which means it's going to have hardly any vapor, which means hardly any vapor pressure. So there's a whole series of thought process, kind of higher level thinking, I think, about this. So there's a lot of different ways they could ask questions using this chart, but if you remember the basics, okay, weakest forces, strongest forces, boiling points, and how that affects vapor pressure, you'll never get a question wrong, okay? All right, so that was good. We're done with that. Let's go over the bookwork now. Here we go, 76. Some of these were kind of review questions, right? They weren't all on the new stuff. Compare boiling and evaporation. I'm just gonna kind of zip through these to save some time. Boiling is when the vapor pressure of the liquid equals the air pressure, right? Vapor pressure pushing up, air pressure pushing down. When those two equal each other, it boils. And what happens when it boils? All the liquid particles can evaporate, not just the surface, and that's what the next part is. What's evaporation? It's when the surface of the liquid gains enough energy to break free of the forces and form vapor. So that's the difference between, well, they want to compare, I guess. So compare means what do they have in common? They both have particles going from a liquid to a gas, right? So that's how they're similar, and then I just went through the differences. But technically compare means how are they similar. I wonder what the book said here. Basically what I said is a little more confusing, but below the surface, they're able to evaporate now, right? If you're boiling, not just surface particles. 78, right? Yes. Yeah. What's the relationship among vapor pressure, atmospheric pressure, and boiling point? There's a bunch of different ways you could answer this. You could say if something has a high boiling point, it has what kind of vapor pressure? We just talked about it. Low vapor pressure. You could say if it has a low boiling point, it has a high vapor pressure. So you could have commented on that. You could also say, as air pressure, atmospheric pressure, Shane, atmospheric pressure goes up, what happens to boiling point? Try again. Yes. So if we have more forces pushing down on that liquid, it takes more energy to push against it. So you need to give it more energy. Does that make sense? So as air pressure goes up, boiling point goes up. Air pressure goes down, boiling point goes down. Right? If you go up on a mountain, boiling point decreases because the air pressure decreases. And the only other thing I could think of with this is that in order for something to boil, your vapor pressure must equal your air pressure. I say that a lot because that's not something that kids just like inherently like memorize because it's confusing. Vapor pressure, remember, is coming out of the water, liquid, air pressure pushing down. When they're equal, it boils. See what the book has, probably some weird answer. That's what I just said. The last thing I said is what the book had. All right, that's it for that. 436. Ooh, wait. 435. Look at mastering problems. Number 81 and 82. Right above it, what do you see? What is that thing called? We just did it in lab this morning. Phase diagram. The only people at a disadvantage right now are people who have lab today. I don't know as if we started. Did we start that today, period 4? Last Friday, did we? No? Okay. Anyways, those of you who have seen that, what's the green area? Solid. What's the yellow area? Liquid. What's the blue area? Gas. Good. What's that little point the dotted line's connecting to? Triple point. Good. All right, moving on. That was fun. 86. Okay. At 25, the pressure is 760, which is standard pressure. The density of mercury is 13.5. Water with the same temp and pressure is the density of 1 gram per milliliter. Explain in terms of intermolecular forces and in kinetic molecular theory the difference. Ooh, I want to hear what someone has to say about this one. How about Dylan?
Mercury has stronger forces of attraction than water.
Perfect. Not much else I could say about that. Good job. The only other thing actually I would say, Dylan, can you comment on how the particles are arranged? So, yes, mercury has stronger or greater forces of attraction. So what does that mean? Very good. That's the kinetic molecular theory part. So yeah, you're talking about how mercury has a greater density. Why? Particles are more closely packed. That's what dense means. And why? Because they have stronger force of attraction. Good. 87. 2 identical containers. Each hold the same gas at same temp, but the pressure inside one container is exactly twice that of the other container. What must be true about the amount of gas inside? Ooh, this is a good one. Makes you think a little bit. So you have 2 identical containers, but the pressure, same temperature, but the pressure inside one is exactly twice of the other. They didn't say anything about the volume of the gas, right? So if you have 2 identical containers, so let's say both containers are 1 liter, okay? But let's say in here it's 2 ATM, in here it's 1 ATM, and they're both at 25 degrees Celsius. Yes, the container is 1 liter, but there's not the same amount of gas in each one. What that means is there's more particles of gas in one of these. Yes, they're occupying the same space, but because the pressure is double here, that must mean something. Hopefully you're following me. Okay, get an idea? I'm going to give you an analogy, ready? Say you have 2 elevators. Okay? One elevator is so full of people that we're stacking people on top of each other. Okay, imagine that. That's this one. This elevator, there's more room inside because there's less people. There's only people standing. We're not stacking people on top of each other. It's weird, but try and go with the analogy. So this elevator, very crowded. This elevator, not so much. That means less collisions, more collisions. So now relate that to the question. If this one has more pressure because there's more collisions, less pressure, less collisions. What does that mean for the number of gas particles in here or here? There's more what? Dense? Where? Okay, why? It's okay if you don't know. It wasn't the greatest analogy.
The particles are colliding.
Well, there's more collisions here, less collisions here, but why?
There's weaker forces of attraction, so there's more gas particles.
All right, forget the weak forces, that's it. There's more gas particles in here. There's just straight up more gas particles. If you have two identical containers, but this one is showing twice as much pressure, there has to be twice the number of particles. There has to be. Otherwise, this is Avogadro's law. Same temp, pressure, and volume. You have the same number of particles in each container. If this was one ATM, you would have the same number of particles in both of these. But because the pressure was double, that has to mean there's more collisions, which means more particles. Because the temperature is constant. So it has to be more particles. I wish there was another way I could kind of explain that. I guess the only way to think of it is if you take the whole lot of gas and put it in a tiny area, it's going to be under a lot of pressure. I think that might make sense to you. If you take less gas and put it in that same area, it's not going to have as much pressure. So that's the concept there. There's more particles, therefore there's more collisions. 89. Solid sugar crystals are dissolved in a glass of water. They form a clear, homogeneous solution in which crystals are not visible. If the beaker is left out at room temperature for a few days, crystals reappear in the bottom and on the sides of the glass. Is this an example of freezing? Laura? No, it is not. Very good. Why is it not freezing?
Because the water inside of it evaporated and left the sugar.
Good, so it's just evaporation. And what the sugar never did this first, Mariana. In order for something to freeze, it has to be in this phase first. Liquid. So the sugar never, if you take solid sugar, dump it in a glass, stir it up, the sugar isn't doing this. It is dissolving. It's not doing this. Melting. You have to melt first before you can freeze. So when you dissolve something in water, it's not melting. That's crazy talk. Okay, it's just dissolving. You have to heat sugar up to a pretty hot temperature to melt it. Okay. Moving on. 90. All right. So I think. Oh, I know what I did. So A and B were 760 because they give you one ATM. So you got to convert that to torr to try and answer the question. You guys might have been able to figure it out because you've heard me talk about it. But anyways, so A and B, instead of 1 ATM, it's 760. And then instead of 0.8 ATM, it's 700. That's why I gave you the numbers there. Hopefully you were able to figure that out. So what is the boiling point of water at 1 ATM? 100 degrees Celsius. What is the boiling point of ethanol at 1 ATM or 760 torr? About, it's like 78 to 80. Different graphs are a little different. So about 78 degrees for ethanol where it crosses that dotted line. And then what is the temperature water boils if the air pressure is 0.8 or 700? So if we drop down to 700, that's the line between 600 and 800. What do you guys say there? Looks like, where am I here? Why can't I read this? It's a little bit below 100, right? What'd you guys say? 98, 99, 98? 98 degrees, right? If we drop that dotted line to 700, water crosses about 98. Okay. All right. Good work with that. You can actually put the books back and then meet me back there. Then we'll come up, take notes for a little bit.